Hey Team Bio, welcome to your screencast on biomes. We are well into our ecology unit, and it's about time we start talking about the definition of a biome. What is it? Well, it's a biogeographical unit consisting of a biological community that is formed in response to the physical environment in which it is found. I'm going to write that down. Okay. A biogeographical unit consisting of a biological community that has formed in response to the physical environment in which it is found. So maybe that's a little convoluted. Let's define it a little bit more. Okay, we live in Vermont and New Hampshire in a specific ecosystem. Our ecosystem is the mixture of biotic living and abiotic non-living things around us. So our ecosystem is full of oak trees and sugar maples and coyotes and squirrels, and where we are is different from Florida, for example, because we live in Florida and New Hampshire are very different physical environments. However, we can find, so in the ecosystem that we live in is consistent with other ecosystems across the globe that have similar physical environments to the one that we have here. Not exactly the same, but in broad strokes they do. So there are temperate broadleaf forests all around the world that are similar to the temperate broadleaf forests that we see here in Vermont and New Hampshire. So I guess maybe that helps clarify it a little bit. We can divide up the entire world into biomes, and there's a predictable pattern to where we find a certain biome across the globe. But an ecosystem is going to be specific to one area. Okay, so the two big factors that impact or I guess the biggest impact on what type of biome we'll find in any specific place in the world is, unsurprisingly, the climate. And the two biggest impacts on the climate are the temperature and the precipitation. And I think that if I had asked you what determines what type of biome we find in any place in the world, you'd probably be pretty quick to say how warm or cold it is and how much water is present. And you would be right. Those are the two things that impact where we find biomes. Tropical forests are places which have a lot of rain and they're quite warm. A savanna is going to be quite warm. It's going to be a mixture of grasses and trees, but it's going to have a little bit less water present than a tropical forest does. A desert is also very warm, but not a lot of water. Chaparral is similar to a desert, but slightly more precipitation and no trees. So a savanna is a mixture of grassland and trees. Chaparral is not going to have, it's going to have shrubs more than trees. A temperate grassland is going to be temperate, meaning not too hot, not too cold. So it's going to be cooler than the chaparral in the desert, and it's going to have slightly more precipitation, but not a lot more. No trees in a grassland. A temperate broadleaf forest is also going to be not too hot, not too cold, and have more precipitation than a grassland. A coniferous forest is going to be a little bit cooler than a temperate broadleaf forest. So by broadleaf forest, we mean trees that have broad, flat leaves are angiosperms. A coniferous forest is composed of conifers, trees with needles on them. An Arctic tundra is going to have less rain than a coniferous forest and generally be cooler. High mountains are composed of both coniferous forests and alpine tundra, so areas with no trees, areas with conifers, and then polar ice is at the very top here. So we can predict where we'll find certain types of biomes based on the temperature and how much water is present. Okay, so what are the two biggest drivers of temperature? The first is, kind of unsurprisingly, the amount of sun that is coming into the Earth. So the Earth's global climate patterns are largely determined by input of radiant energy from the sun. Okay, so if we look at this image here, there's something I want to draw your attention to. It's that this band of energy from the sun, and this band of energy from the sun, and this band of energy from the sun, they're all the same size. So this is showing us, and then we could do the same thing here and here as well. All of these bands of energy from the sun are the same size. This means that this amount of sun has the same energy as this amount of sun, which has the same energy as this amount of sun. But if you look at the Earth, you can see because the Earth is curved, when we take this amount of sunlight energy and we strike it on the Earth, it takes up this much space of the Earth. Whereas if we take up the same amount of sunlight energy and when it's incident upon the Earth here, we see it spread out over a much larger area. So because of the Earth's curvature, there's an unequal distribution of solar energy. The same amount of sunlight is spread out over a larger area at the poles. And the area near the equator absorbs more heat in comparison to northern and southern latitudes because it gets more energy from the sun. So that's a big takeaway. Dependent on where you are in the world, the same amount of sunlight is going to be spread out over a larger area. And so, unsurprisingly, things near the equator are hotter. Another big driver of temperature is the, and so this is going to be true all year long. Because of the low angle of the incoming sun, we just have more spreading at the poles, and it's going to strike more directly at the equator. Another factor is how much sun we're getting on a day-to-day basis. So you all know that we are approaching the dark times in New Hampshire. When we reach the December solstice, which I believe is on the 21st, but it might be the 22nd. Anyway, somewhere in late December, it's going to be the shortest day of the year. And this has to do with the tilt of the Earth. So the Earth is tilted about 23 degrees. I think it's 23.5. So 23.5 degrees off its axis that it's spinning on, which is this axis right here, this little line, is tilted 23.5 degrees from the sun. So I think it's easiest to imagine that you're standing right at the North Pole up here. And when it is the longest days of the year, the shortest days of the year up here at the North Pole, you'll see that this spot where we have our imaginary axis line going through the Earth, it's going to spin here around like this, and someone standing right at the North Pole will always be in darkness. Someone standing at the South Pole will have an area or have an all day, it will always be light here. And so These are the longest days of the year for people living in the southern hemisphere and the shortest days of the year for people living in the northern hemisphere. During March and September, because the sun is facing the equator directly, no matter how we spin this axis, everybody has length of days the exact same. So we have a 12-hour day here. As we move towards June, so as the Earth moves around the sun in its orbit, we are going to approach the June solstice, and people who are at the North Pole are going to have days that are without nights. So imagine being here up at the North Pole, and when we spin this axis around like this, the sun will never set. It will always be light up here. And then we have areas of the South Pole, which will be in total darkness, like we had here in our winter. So these are the longest days of the year in June. So this just means that we're getting more sunlight coming in because we have a longer day in the summer rather than the winter. Okay, so and the equator obviously has pretty consistent days. They don't change much over the course of the year. The closer you get to the equator, the less variation you have in the length of your day. Okay, so these are two things that determine the amount of sunlight. Another thing that has a big impact on the temperature is the altitude. So if you've ever been for a hike in the 4,000 in the White Mountains, 4,000 footer, you'll know that on a balmy day in the fall, down in the valley, maybe you're in t-shirts and shorts, and then you reach the summit of Mount Washington, and it's quite chilly. And this is because the air temperature drops by about 6 degrees Celsius for every 1,000 meters in elevation that you increase. So the amount of sun that's coming into striking the Earth affects the temperature, but the altitude that you're in does as well. So these are two big impacts on the temperature. I realize that I'm doing a lot of talking and not writing things down, but you should write things down that I'm saying. Okay, next let's talk about precipitation. So we see bands of areas where we have a lot of precipitation, and then bands of areas that we have very little precipitation, and it has to do with where we see the most amount of solar radiation. So right at the equator, we see the most intense solar radiation. So because of that, there's going to be a lot of evaporation that happens here. This is water that is in a liquid state turning into a gaseous state. So water evaporates because there's a lot of heat created by the sun, and warm air can hold a lot of moisture. So the warm air that's down here absorbs a lot of moisture, and then it rises because it is warm. As it rises, you know that as something goes up in altitude, it starts to cool. And as it starts to cool, it can't hold as much water vapor. And that water vapor condenses and forms rain. So this ascending air, as it is going up and up and up and up, it is precipitating more and more because it can't hold on to as much water vapor. Okay, so now we get up here and we have cold air, which starts to fall again. But now it's dropped a lot of its moisture, so the cold air that starts to fall is very dry. And it is going to, as it descends and warms up again, it is going to absorb water that is in the land. So we get these bands of across the world. This pattern is going to repeat itself one more time up the world, where we have a lot of evaporation and then precipitation, and then areas where this dry descending air is going to absorb a lot of moisture, so patterns of tropical rainforests and then big deserts. And if you see here, across the world, we see areas where we have tropical rainforests in the middle here, and then deserts in the Tropic of Cancer and the Tropic of Capricorn, because this dry air that shed a lot of its moisture is now absorbing moisture from these parts of the world. Okay, so this is big pattern that is determining where we see the most precipitation and where we see really areas of dry. Another big impact on the how much precipitation we see is mountain ranges. They can cause a rain shadow. So what happens here is we have evaporation that is happening over the ocean. And as warm air that's holding a lot of moisture is blown in from the sea over the land, it is forced up over a mountain. And you know that when you climb a mountain, the temperature drops. So as the temperature drops, the amount of water vapor that the air can hold goes down, and we get rain. This is more, even more dramatic if a mountain range is really big. We would see not only rain, but also snow. So the higher up the warm air is forced, the more precipitation it will drop. And as it flows over the mountain range, then it's dropped all its moisture. And so as it descends again and warms up again, it's very dry. And so again, we get this, we're going to get absorption from the land by this dry air that has shed all of its water vapor. So we see rain shadows anywhere that we find a giant mountain range. So you can see here we have a rain shadow that occurs after the Sierra Nevadas. We see a rain shadow following the Andes, and a rain shadow on the other edge of the Himalayas. Okay, that is all.